let's look at this problem here. And again, I gave you, you've seen this problem already. So suppose that you have a positive charge here. And let's say that this is 3 microcoulombs, 3 microcoulombs. So this is point P here, such that the distance from here to here is 1.0 centimeters. The distance from here to here, 1.0 centimeters. And the distance from here to here, 1.0 centimeters. Now, I gave you this to try at home, right, to calculate the force. So remember that last time we had a charge here, Q naught. We put a charge here, Q naught, that was equal to 6. You guys remember this? So what I want you to do is that in your next try at home problem, I want you to first calculate the electric field at point P. Then once you've obtained that, calculate the force on 6 microcoulomb test charge. You're going to get exactly the same result. So when I say calculate the electric field, I want to see magnitude and direction. Again, if you remember, if you do this correctly, you're going to get an electric field pointing in the J direction. So you're going to solve this problem exactly the same way that we've solved. So when you solve this problem, you're going to say that these two charges here, those are my source. So I have two source charges. I want to calculate the electric field at that point. Then once you know what the electric field is, you can just calculate the force. So you're going to get your force as, so this will just be Q naught, the electric field at that point. Where Q naught is this charge right here, 6 microcoulomb charge.
So with that, do we use like the hypotenuse to calculate the distance between the charge, the source, and the test charge?
Yes, yes, because all right. So why don't we go ahead and let's just kind of let's solve this one. So I'm not going to solve it completely, but let me just kind of show you how to solve this. So let's say that the distance we know, so this is my point P right there. And I know that this is 1.0 centimeters. This is 1.0 centimeters. This is 5.1. So this is 5. Let's call this charge number 1. Let's call this charge number 2. All right. Then I'm going to make a table here and ask myself what is given in the problem. So what is given in the problem first? I know what my Q1 is. So my Q1 is 3.0 microcoulombs, which I can write as 3.0 times 10 to the negative 6 coulomb. And Q2 is 3.0 microcoulombs. Again, I can write this as 3.0 times 10 to the negative 6 coulomb. My Q naught is 6 microcoulombs, which is 6.0 10 to the negative 6 coulombs.
In this formula, do we always have to convert it to coulombs?
Yes.
And not use microcoulombs?
No.
Okay.
Unless sometimes if I say that calculate the charge, I can say, give your answer in microcoulombs. But if I don't say that, then we always need to put in the standard unit, which is coulombs. Now, You know this KE value here is equals to, we can use it as 9.0 times 10 to the 9. This is in Newton, meter square, Coulomb square. Then, so if this is my charge number 1 and this is my charge, let's calculate this distance here, and I'm going to call this distance R1. So R1 is going to be 1.0 squared plus 5.0 squared, that gives me 26. You take the square root of that. So R1 is going to be, so R1 is the square root of 26. This will be in centimeters. Now I want to write this as square root of 26 times 10 to the negative 2 meters. Because we need to get our distances from centimeters to meters. Then my R2, which is the distance from here to here, is also the square root of 26 times 10 to the negative 2 meters. All right, so now I need to define these two vectors here. So this is my one direction here, and this is the other. So if I want to do that, I can say that let this angle be equal to theta, which is the same as this angle right there. Then if this angle is equal to theta, then you're going to notice that, for example, so this angle right there is also equal to theta. So when I write down my electric field, I should write it as, let's see. Let me get rid of this. Instead, I want to call this. I mean, you can solve it the way you want, but let's call this theta instead, so that this angle here is going to be equal to theta. So it means that I can write. So let's write my. So E1, which is the electric field from Q1, is going to be E1, so KE Q1 divided by R1 squared. And the unit vector pointing in that direction is going to be cosine of here I hat plus sine of theta j hat E2. So E2 is going to be KE U2 divided by R2 squared times, now if you look at this direction here, it's negative cosine of theta I plus sine of theta j. Now, if you add E1 plus E2, add these two together, notice that the cosines are going to cancel. And this will give me, now because Q1 is equal to Q2, this will just give me 2 KE Q1 over R1 squared sine of theta. You see that I have everything to calculate my electric field. I just need to get sine of theta. So let's look at this picture here. So sine of theta is going to be equals to 5.0 divided by square root of 26. So I have everything that I need. I have KE, I have Q1, I have distance squared. I can calculate the sine of that angle. So all of this is the electric field. So this is the electric field at that point right there. So this is part A. So I'm just going to leave it like that because I don't have time to substitute all the numbers, but you can plug in those numbers. So if you plug in your KE, you plug in your Q1, you plug in your R1, you plug in your sine of theta, you're going to get some value. Now, when you do this is going to be something, so the unit for the, I didn't mention this, but the electric field is going to be in Newton per Coulomb. That's the unit.
What happened to Q2 in this?
Okay, Q1 and Q2 are equal, right?
Oh, yeah. Okay.
Yeah. So what I've skipped a few steps right there.
Yeah. I forgot they were equal.
Yeah, so this is, so from here, so going from here to here, what I've done is that I'm saying that you have, there's a cosine here, and there's a negative cosine here, so those will cancel. Then because Q1 is equal to Q2, right?
You just multiply 1 by 2.
Yeah. Okay. Now, so in the past, when I've had, so in the first exam, what I do is that I've taken this problem, I can change it in different ways, right? So what I've shown you here is just a really basic example, but I can show you, if you guys are done with this picture here. Okay, so we have a question from online. It says that, why is the second cosine negative? Now, the second cosine is negative because, again, if you look at this point, so let me open, I'm going to go ahead here and open, so let me open a different picture here. So again, this is my Q1 and this is my Q. So let me really draw the vectors here so you guys can see. So this is point P. Now, because this is Q1 and this is Q2, now we said that the electric field from Q1 must be a line that is pointing in this direction like that. And the electric field from Q2 is a line that points like this, right? Now, because this angle here is equal to theta, it means that this angle is also equal to theta. So it means that when I calculate E1, I can break it into X and Y, right? So the X component is cosine of theta, and the Y component is sine of theta. Now, when I calculate the electric field for E2, the X component is negative cosine because it's pointing to the left, and the Y component is sine. So this is why there is a negative on the cosine. Does that, all right? So as I said, I decided to use this angle as my theta, but feel free to use this as well. It's not going to change anything. If you wish, you can call this theta, right? But if you call this theta, then it means that your X component is going to be sine and your Y is going to be cosine. So just be consistent on what you use as sine and cosine. As long as you know what you're doing, you should be good. Okay. Now let me show you a few more. I'm not going to ask you to solve this at home, but I just want to show you other problems that now one could be something like this. So you have a positive charge here, a negative charge here, and then my point P is actually right here on the x-axis. Let's say this distance here is 1.0 centimeters. And this distance here is 1.0 centimeters. And the distance from here to here. When you solve this problem, so this is positive. Positive, positive, again, 3 microcoulombs. Now, when you solve this problem, it's going to be the same thing. The only difference here is that your electric field is going to be pointing in the I-hat direction. All right. So look at the problem very well. Q1 is equal to Q2. Distances are the same. It's very easy for me to solve that problem.